Pete is our first presenter this morning. He's he's a professor of physics at the California Polytechnic State University. He's studied global poor and cooking since 2007. This has included improved biomass stoves, solar concentrators, and latterly solar electric cooking. In 2015, Pete developed an insulated solar electric cooker where the solar panel was directly connected to an insulated electrically heated cook pot. I have an idea we might have a slight demo or a demo as part of this session. And they were funded as part of TRID to enhance this cooking pot with a phase change material that would enable cooking to be undertaken beyond dusk. So I'm going to hand you over to Pete. As with all of these sessions, if you have questions, can I ask you to put them in the chat room and we'll come back to them after our second speaker is presented. Thank you. Thanks, Pete.
Ready to start?
Yes, please.
Excellent. Okay, so you can cook food directly with a solar panel, with a 100-watt solar panel. That's relatively inexpensive. 100 watts will bring about 1 kilogram of water to a boil per hour. So in the course of the day, a family could cook 5 kilograms of beans and rice, enough for their whole family. However, with 100 watts, you can't even bring water to a boil because it cools unless you insulate it. So we insulate it very well, and we try these out. And people say, we want more power. We don't want to spend all day cooking, and we want to cook after dark. So what if instead of directly heating your food all day, you melted a phase change material and stored that thermal energy all day long, and then at night you could throw the food into the cook pot and cook it pretty quickly? The phase change material we use is erythritol, a sugar alcohol. It has a melting temperature of 118 Celsius. Its heat of fusion is slightly more than that of water, which is really great, and its specific heat in the liquid state is slightly less than that of water. So how does it work? Well, let's give it a try. Now, can you see my screen? You should be able to see me.
We can see you now.
Oh, you can see me. Great. Okay, so then you see this white up in the corner of my house. It comes down to my cooker. And right now it says it's about 153 Celsius. And I open it up and it's hot to touch, so I'm quick, and we can dump some olive oil in there. And the temperature, begins dropping somewhat. And I can throw in some onions. And you should be able to hear, we're cooking along pretty good. So if I stir that up and leave that, and it's still hot, so I'm going to be quick. Let me put this down. And let's see, I'm trying to get back to my talk. There we go. Okay. And we'll get back to that. Now you can see my screen again?
We can, yeah.
Yes.
Okay, so I've made a mistake here. We have to go back to presentation mode. And so what I'd like to express is that in using it on a regular basis, it's going to take a moment to load again. In using it on a regular basis, we run into situations where, like, I'll say, this sucks, I don't like it. And that leads to a lot of innovation for us. That's how we've made a lot of our progress, because through the use, we have problems that we can change. And so one of the takeaways I give my students is that the people who are producing, who are building, who are innovating should also be using the technology on a regular basis. And so that's one of the things I give to you as well, is that if you're trying to develop a winning technology, it's best if you yourself are using it, because one, if you run into problems, you can fix them. And two, if you say, I don't want to use this technology, it should mean something to you about the success of this technology for other people to use. And so it's not just me who should be using it, because there's all kinds of cultural challenges everywhere. And so we're developing this technology with a global learning community. We have a research group in laboratory, and we have a dissemination group. And Cal Poly is partnering with Eastern Illinois University and with field collaborators in various countries, Africa and India. And so rather than go in with economies of scale in an industrial setting, our idea is to have local enterprises develop the technology and disseminate it locally. And the benefit of this is multifold. One is the salary and the resources are inexpensive in low-income communities. Also, now we have diverse designs because of the different access to resources and cultural preferences. So we're getting all of this different information on how to innovate the technology. A good example is one of our collaborators from India says, we have an aversion to using aluminum because of a history where people were poisoned with lead-laced aluminum. So we won't use it. And we're like, okay, then we have to find a way to use stainless steel there. Also, we support the local economy, which we think is great in low-income communities. And lastly, what we're doing is we're building local technical expertise because the people there are learning how to build these. And this has two benefits. One is in product support. If there's a problem, they're going to be able to fix it. And two, we're building, the local education for people to move into to technical development on their own. And so our support is twofold. Financially, we subsidize the beginning of projects by providing $1,000 for any company we think can produce ISEX, and then $4,000 for subsequent development. And technically, we have a construction manual online that's a living document that a bunch of students are continuing to develop with new findings. We have a forum for questions and answers and knowledge sharing, and we have weekly meetings every Tuesday morning. You're welcome to come anytime you like. In England, that would be probably early afternoon. At Eastern Illinois University, we're developing a cooking lab. They're going to have 5 ISECs up and running in January of 2021, next year. And so let's talk about some of the challenges. So erythritol doesn't always crystallize at 118 Celsius. It's called supercooling. And so what you see here is over a period of about 7 hours, 8 hours, we have a hot ISEC. This is the blue is the inner pot next to the food, and the red is the outer pot toward the insulation. And it's slowly cooling with the power off. And then at this moment, we add a kilogram of water. And what you see is immediately the entire phase change assembly with all of the erythritol drops well below the crystallization point and follows that of water. And then after an hour and a half, something initiates the crystallization. And then in about 15 minutes, 10-15 minutes, the temperature jumps back up to 118 and slowly drops. Now, this is a problem. Actually, what we found with our innovations is it really isn't a problem. If you look at this, first of all, the water still boils in about 20 minutes. And as it crystallizes, the water keeps to a low boil over the course of 5 hours. So you could slow cook something for a long period of time. And lastly, we're exploring ways to initiate the crystallization ourselves. For instance, we have a dipstick now, a wire that I could show you in here, that if you pull it out, it cools and develops a layer of crystals, and you can put it in to seed the crystallization. So actually, supercooling is our friend, because if you can let the temperature drop without it crystallizing, then you lose less heat to the outside world. And then it can crystallize on command if you can make it happen. And there's a number of different ways to get it to crystallize, and we've had really positive results in this area. The real problem that we're running into is material degradation. It's a harsh environment at 190 Celsius, and we can see that the aluminum coated mylar doesn't last very long. So we need materials, and maybe you can help us out, that are inexpensive, thermally insulating, and thermally robust. One of the things we're exploring is using a double-walled vacuum cooler. And it is not inexpensive. Between all the parts, it's about $70. But we're reasonably confident. I'm confident that if we bought 100,000 of them, this cost would come down to probably in the 20s. Lastly, the erythritol itself degrades. So what we're looking at, and so we're exploring that as well. And I got to tell you, what we're learning about erythritol is way, 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 way more interesting than we wanted it to be. So if you look at this over the course of 20 hours, we let it cool, and it super cools to 94 Celsius, still pretty hot. And then it crystallizes to 105, and for some reason we don't know, crystallizes again to 118. And so what we note is there are two crystallization temperatures. And looking through the literature, I did find this published in one place where there are, in fact, two temperatures. And what we see is a slow transition here over 3 hours, but a sharp transition here over 15 minutes. But after 4 months, because I've been using this now almost every day for 4 months, we find that all the temperatures drop. What you see here is it super cools further to 75 Celsius. And rather than 105 and 118, it's 95 and 212 now. And so is this a problem? Well, actually not yet. You can see that we induce the crystallization by cooking. Here we cook. And we could induce this crystallization if we wanted to bring it up to 112. And so right now it still works to cook. And in a worst case scenario, potentially we would have to change the material every year. And so we have a group of students on the dissemination team, and they're distributing questionnaires to study adoption, and they're generating GIS maps about the environments that we're working in. And I have some service learning project-based groups in sustainability classes. You're welcome to check this out. And there are 4 groups dedicated to working with some of our field collaborators in how they're disseminating, or how they're right now developing the technology and disseminating it. So thank you very much for your attention. I hope that I was reasonably close to 10 minutes.
I think that was pretty spot on, Pete. Thank you.
Great. Now, if you want, in a minute, I can. Should I throw in the broccoli and see how things are going with our?
That sounds good. I think there's a bit of time before we'll move to John, but I'm interested to see where you've got.
You need to turn off screen sharing, John, Pete. Pete, turn off screen sharing because we're not yet back on you.
Oh, okay. How's that?
That's better.
Okay, you can see the onions are cooking away there. Yeah, they're a little bit browned. It would have worked better if it were hotter. But you know. And so what we can do, we can throw in the broccoli here, and maybe during the question and answer session, we'll check in on the broccoli and see how this is cooked.
That sounds good. Yeah, thank you.
Okay. Take it away, John.
Okay, so I'd like to introduce our second speaker for today. This is John Mullet. So John is the Managing Director of SOWTech, which is Sustainable OneWorld Technologies. So SOWTech are a UK-based community interest group, and they work with companies, charities and NGOs in the global south. So they use their knowledge and expertise to help transform the lives of people by developing products for a more sustainable and a healthier way of living. And this has included waste management and biogas production in the past. And we funded their project for a clean cooking appliance via TRID, which completed in March. And likewise with Pete's project work, you can find the reports from both of those on our publications page of the website under TRID Challenge Fund reports. So I'll hand over to you, John, if you're ready. Thank you.
Welcome to this presentation entitled Delivering eCook at Ground Level. I am John Mullet, and I work for a social enterprise called Sustainable OneWorld Technologies, or SOWTech for short. Our mission is to create income-earning opportunities for sustainable development in hot, low-income communities. Most cooking in sub-Saharan Africa is undertaken on the ground using either a 3-stone fire or an improved biomass cook stove, such as those shown in the photographs. The aim of the project was to develop a solar-powered cook stove system that was both affordable and acceptable to low-income families. Our strategy to achieve this was to design the components of the system so that as much as possible could be built locally. Bringing another imported product from a factory in the Far East is not, in our opinion, the best way to serve the poorest people. Let me break with tradition and put our acknowledgements up front. Firstly, we would like to thank MECS for giving us the resources required to undertake the project. Secondly, we would like to express our thanks and appreciation for all the help that our partners Aquaid Lifeline provided to the project. The folks at Aquaid's Namisus Children's Village were generous with their time and support during our initial user-centered design study and then subsequently in the field trials. They helped us with information such as what time of day they cooked, what they cooked, how many people they cooked for, and how big were the pans that they used for these meals. However, the strongest message we received was the importance of integrating a phone charger. The suggestion was that the men would be influenced by such a feature as well as the women, thus helping to achieve social acceptability to this change of cooking. So, if we want to choose when to cook, we must find a way to store solar power. There were a number of storage options considered. We decided that batteries to store electricity were too costly and too difficult to maintain. They had a limited life, and the environmental issues associated with the end-of-life recycling were problematic. We decided that heat-retaining metal structures, such as the Argus stove, would be too difficult to build and insulate and transform. We decided that concrete or clay-type structures would not be able to hold enough heat to deliver the heat for cooking. We did choose to use phase change materials, or PCMs, to store the solar until it was needed for cooking. The phase change material we chose was erythritol. It has been successfully used in earlier work by Professor Schwarz and his team at Cal Poly. It releases heat at 118 degrees C. It is mass produced as a sugar alternative. It is readily available, and it is a food additive, so safe to use in the proximity of cooking. And it is a fermented product which has the potential to be produced locally. In the graph on the slide, you may be able to see a blue line which shows the temperature of the PCM. During heating, it rises. Once the heating stops, it falls and then flatlines at just under 118 degrees C. This lasts as long as it takes for the PCM to solidify. The heating and cooling cycles can be repeated multiple times without degradation. To achieve our affordability targets, we needed to change how we use the PV power. We developed a device to replace the regulators and batteries required by most PV-powered systems. This means that the solar power is used directly from the PV panels, rather than indirectly through batteries. There were three parts to this work: the thermodynamic calculations, the development of the power optimization device itself, and the research concerning the availability of PV panels and their specifications in Malawi. The graph illustrates the stable draw of voltage from the panel whilst delivering variable voltage to the heater, and the pod can charge a phone. In order to cook, the electricity from the PV panels needs to be converted into heat. We built and tested a wide range of heaters based on using materials available in Malawi. A resistive wire heater and a temperature sensor are encapsulated either between two ceramic tiles or embedded in clay and then fired. The picture on the right shows an infrared test of a clay heater. These heaters were inexpensive and could be made locally. We designed and built a cooker in Malawi which housed both the heater and the phase change material for heat storage. As the photo shows, the heater was wrapped in a blanket to enhance the heat retention of the oven. Sitting next to it is Lupaccio, a student from the village who spoke English. Later, he spent time explaining to Raja, the guard, how the system worked. We were pleased to have achieved some cross-language understanding of what we were doing, as we considered local engagement to be a very important part of what we were doing. After all this work, we did also do some cooking using our platform of direct-use solar. We did cook ensima, a maize flour dish. We also did some work with a hot plate, as the video shows. So, are we continuing things after the MECS project has finished? The answer is yes. We have secured other funding to allow us to design and build and test a Mark II pod. With a number of African partners, we are currently working on the following: preparing the training program to start manufacture of the pod in conjunction with partners in Africa. We are developing performance insulation products to use both with the cookers and cooling applications from materials found in Africa. We are seeking support for building a modular agro-processing hub using direct-use solar for crop drying in partnership with a consortium of 20,000 smallholder farmers. We're using direct-use solar for heating technology to improve the performance of anaerobic digestion, which is treating fecal sludges, and we are using the solar platform to create proactive evaporative cooling for agri-product storage. On behalf of the SOWTech team and our partners, thank you for watching. We would welcome any questions or further contact.
That's great. Thank you, John. We've got a few questions in the chat. If I can kind of direct them to you and answer them for me if possible. So Pete, my question actually is about, you mentioned the recycling and degradation of the material and that you may need to replace the material annually. So I know that you had problems sourcing erythritol locally, and wondered what the impact of that would be on cost and whether replacing that material annually would impact on the cost effectiveness of the system.
Yeah, great. So I saw the question also on the chat, if we're just, exploring it, and I felt some frustration because I couldn't figure out how to answer it, but then I let it go because I wanted to pay attention to John's talk. So yes, we are actively investigating phase change materials. I have one student dedicated to that, and maybe another. So there are a number of things we can do. Erythritol is the best phase change material that we've run into, but we're also looking at magnesium chloride hexahydrate. And we've tried it a little bit and it doesn't work very well, but it might be the sample we got, so we're looking at it more. Magnesium chloride hexahydrate is toxic to the point that if you put it in your mouth, it'll burn your mouth, but it's not, in small amounts. Like if it got into your food for some reason, it wouldn't hurt you. It doesn't have the same ability to hold heat. It's not, it's its heat of fusion is not as high. It can go much higher in temperature and not get degraded is what the literature shows. So we're exploring that. But at the same time, even with erythritol, if it continues to degrade the way it has been so far, it appears as though it'll work pretty well still. Also, we could just lower the temperature for it and not run it up to 190 Celsius, but just run it up to 170 Celsius, and it will probably not degrade. On paper, they say it's stable up to 160 Celsius. But we keep in mind that this is from the food industry. So their quality control is going to be much, much higher than ours. As long as it crystallizes, we're fine. So there's a lot of leeway. And yeah, we're looking at a lot of, not a lot, we're still looking at different phase change materials. There's another one, actually, xylitol, that supercools all the way down to room temperature, which is a problem unless you can seed the crystallization. And that actually is robust to higher temperatures, so it would work better at the high end. I mean, the truth for me in using this every day is that, I was initially really concerned about supercooling and having the transition temperature higher. And in practice, it actually doesn't matter, because there are two regimes that I use. One is the high temperature regime where I cook and I want to saute. And the low temperature regime is where you might cook beans overnight. And so when I want to fry, it has to be hot, and we're using just the sensible heat in the hot erythritol. And then as it begins crystallizing, the power drops way low unless you're trying to heat something that's really cold, like room temperature water. And the heat flow is really low, and this allows you to cook for a long period of time. So, in fact, where I was very concerned about the supercooling and the crystallization temperature, in fact, the way I use it, it isn't really that much of a concern for me.
Okay, and I guess if it's not a concern for you, then cooking within communities isn't going to be an issue either.
Well, I wouldn't want to jump to that conclusion completely, but it's just that there's so many different facets that will open up when we start getting these out in people's lives. For instance, one of the innovations in India was they said, well, eggplant is awful with an ISEC, our partner Hawazin. And I said, really? Now, that's very surprising to me, because I cook eggplant in mine all the time and I love it. And she said, well, the coconut oil just tastes like mush. The texture is all wrong. And I said, could you cook with vegetable oil? And the anthropologist furrowed her brows at me, and she kind of like shook her head. Why would we want to cook with vegetable oil? And so we've had a huge amount of discussion about that. And she said, I think it's a non-starter. People want to use coconut oil. And I said, okay, well, you could try to cook, toast the coconut oil first. But there's also the option of saying we can't cook with coconut oil with the ISEC. So then you would cook your stews and your rice and your beans with the ISEC, and you would limit your fires to your sauteing, to your high temperature cooking. And and then maybe over time, if people have an ISEC, they might explore different ways to use it. So there's just, and then there might be other communities that would use it differently. So I wouldn't jump to the conclusion that because it doesn't matter for me, it's not going to matter for other people. But I think that, cooking is so multifaceted. People have so many different cultures, and so what we want to do is just learn as much as we can about this and get them out there and see what happens.
Sure. Yeah. So John, did you find, sorry, I was just going to ask if you found differences, because you were cooking in Malawi. No, you were cooking in Ghana.
Malawi. Yeah.
Malawi. Okay.
I mean, a couple of points there to back up what Pete's saying. I'm really interested to see your data on the temperature degradation, Pete. That's new to me. That's really helpful. We on the comment there about the erythritol, we put a temperature limit on our units to 150, which may be one of the reasons we haven't noticed it in the same way as you have. That's really interesting, but that's quite easy to do, as you say, because obviously over 120 it melts. The other comment, really, I was reinforce again what Pete was saying there about feeding or cooking patterns. One of the things that we found our approaches really suit very well is slow cooking, and that's something that culturally we're quite familiar with. It is not something that culturally our Malawian partners are familiar with. You know, you wouldn't leave a fire cooking on a pot overnight, you know, and try and keep the stove going. So, but if they had the facility to do it, maybe that would be a good way of preparing their sauces and things. So time will tell, and as you know, application is really what matters. So yeah, just reinforcing a couple of points there.
Now, John, if I could ask, slow cooking, you say is something that they don't do, but yet they boil and simmer cook quite a bit. Is that correct?
Yes.
So,
but the key to that, to me, though, is the real challenge of cooking beans, because you've got the phytotoxic compounds, the toxic compounds in the beans that have to be boiled first, and then it takes a long time to make the beans digestible. So in just cooking their plain black beans, you've got two parts that need doing. So the boil cook isn't really suitable for the erythritol, you know, because it's quite hard to bring it to a rolling boil, whereas the second part is. So that would, but they do cook a long time for some of those things. Yeah.
I don't understand. Like, to me, erythritol is perfect for that. You said it was hard, right? So like when you put the water in, it comes up to boiling reasonably quickly because the water is so much colder than the erythritol, and then the erythritol is there and maintains the boil, is what I thought.
Yeah. I mean, the erythritol starts to cool in proximity to the water, as you pointed out. So maintaining the key to degrading the bean toxin is what I'd call a heavy rolling boil. And we found that putting the water in, it brought it up to temperature just before boiling, but it didn't produce the rolling boil.
I see.
So it could be heat losses and heat transfer calcs, but these are things that we can work on.
Yeah. So you need a roiling boil. It can't boil. So if it just boils at a low level, that's not enough to kill the toxin in the beans?
Yeah. Well, it's arguable because it's a time temperature thing. Yeah. But it only takes about 15 to 20 minutes of boiling to detoxify the beans. Now, I think there'll be variables on types of beans and so on, but it's something we need to be careful of with that particular vegetable.
So what if it boiled at a low boil for 3 hours? Would that do it?
The data from my limited research isn't available to do that, but I'm told it's actually worse. My reservation is that actually it can make it. There are documented cases of upset tummies and things because of slow cooking. If you read the cookbooks that I've checked out, they don't recommend slow cooking. Now the slow cooking at 50 and 60 sort of sous vide temperatures, but there's slow cooking at 80, and so to me there's a world of investigation there to still go.
I meant slow cooking at 100.
Yeah, that isn't available. I haven't found that information yet.
I see. See, and the reason I make a big deal about this, John, is because, this is really convenient for me. Like, I actually rarely use a different cooking technology in my kitchen now, partly because I want to explore this. But for boil and simmer cooking, the direct cook without phase change material works perfectly. You throw it in the morning, it never burns. It's always very thoroughly cooked in the evening, as long as we have sun, right? And it always comes up to 100 Celsius. And so I recognize the phase change thermal storage is sexy. That's what everyone wants. But actually, for utilitarian, the direct heat is so inexpensive. It's so solid. It's so easy to build that, you know, this is what I think would make the biggest difference.
I very strongly agree with the comment that was made yesterday, and that was that heating water is probably the biggest single factor that we can do.
Right, like over a period of time, you could bring a big chunk of water to a boil, and then you could throw your enzima in it, or, you know, cook whatever you want with the boiling water.
Yeah, and the comment was
so maybe that's something that, you know, certainly this does it with the phase change, it does it without the phase change, but potentially if what we are doing is bringing water to a boil, there may be some way to further optimize the system if that's really what it's going to be used for the most. Yeah.
I think something that you just commented on in your talk too, that I feel very strongly about is that I think the next agenda is going to be insulation.
So this kind of moves on to my point. There's considerable evidence from the TRID projects about insulation and the importance of insulation. So at the moment, I'm in the process of undertaking a review of all of those reports, and they'll be published on our website when they're complete. But insulation is kind of one of the keys for cooking moving forward. Can I just ask, we've got a couple of questions that have come into the, can I just kind of move the conversation on? As fascinating as it is, guys, but I don't think anyone's got anything to add about cooking temperatures for beans. I'm sure they'll jump in if they have. So it's a technical question about the design of the power controller, and wondering whether you've actually published that information. So I think that's kind of more specifically aimed at you, John, with your pod, so the power controller that you developed. I know there's a little bit of information in your final report, but have you produced any kind of designs for that controller?
Yes, we are happy to. We've passed across to Pete the printed circuit board diagrams and the like are available if anyone would like them. We haven't put that into a publication yet because we simply haven't published it. Are working on an open book basis with that controller, yes, and the intention is, and this is what we're currently working on, that it has been designed with a level of sophistication. Sorry, I'll start again. In order to build it, we have chosen techniques in the design of the kit that it could be soldered together from components and a printed circuit board by somebody with a relatively basic level of manual skills in that area, sort of high school level soldering. So it is something that we want manufactured in country and from components that have been brought in, rather than a pre-manufactured piece of kit, which obviously could be bought in from an electrical fabricator. Have I made myself clear? Probably not.
Yeah, no, that's great. That explains kind of explains and expands on the question. I think I'll link you up with John, who's quite keen to get the design for your controller. But you've led me on to the next question, which is about creating jobs. Could
I respond to your question to John for what we're doing?
Yeah, sure.
So I have two students working on a microprocessor that would optimize power from the solar panel, as well as provide some electronic control. And, you know, I mean, we may have great success, we may not. But there's another possibility, and that is to have no electronic control, because what's happening with the cost of solar panels now is that for another 20, you know, in another year, it's not unlikely that another solar panel could just be another $20. And so if you put two solar panels in parallel, you're not using the power optimally, but you're getting the same amount of power that you'd be getting if you had a power optimization device on one solar panel. And, you know, in the future, the solar panels certainly are going to get cheaper. And so we're working on it as well. But also, John, I can say we've already submitted for publication our phase change thermal storage and to solar energy, and it got rejected. And so we're working on, you know, pending improvements. But a month goes by and we make more findings, so we're updating it. So we're also on the road to trying to publish what we're finding.
Great,
thank you.
Yeah. John, does that answer your question, John Barton?
Yes, that's great. So yeah, I've got something quite similar in the next few months. So yeah, that's great.
Thanks. Hook you up with Pete and John and kind of help move that forward.
Sure. John, you can tell me what you're developing, or should we take that offline?
Probably take it offline. Initially, I'm just doing a AC system, but then yeah.
Excellent.
I'm happy to kind of link you guys together, so I'll do that after the call. Can I ask another question that relates to job creation and cheaper appliances? So this has come from Simon, and he's asking, the core to your work is the idea that local made creates jobs and ends up cheaper, but it competes with imported products that are aspirational and slick. At the moment, you have described to leaving the evolving designs to local artisans. But do you foresee a moment when the product design students will get involved and make your products slick?
Shall I go first?
Yeah, that's great.
Completely agree that we should try to drive as much value in jobs and work as low as we possibly can. The designs will always evolve. The challenge will always be cost, slickness, and capability as a balance. From our point of view, the more people we can have making these devices so that solar power is available, the better. And yes, of course, I imagine that some of the projects will then evolve into different directions. I mean, we have already evolved ourselves into controlling of temperature management by the addition of one sensor for heating digesters. You know, we don't want the digester to go above 38 degrees centigrade, so you just put a sensor in and then it puts that limit on it. So that's an evolution of the design. So nothing stays still, and yeah, I look forward to it getting slick. And I agree, it's a real challenge between making things happen because they are aspirational, you know, Tesla being the finest example, and making things happen because they're affordable. So our ambition is that people will earn a living fabricating these devices and providing these solutions and creating their own infrastructure. I don't know if you want to add anything.
Me?
Yeah, have you got anything to add, Pete? Because I know your system was to be produced in country.
I agree with John. I think we're very similar minded about you know, our dissemination model or our scale up model. As far as being slick, I think the thing where my student developed with the vacuum flask is already pretty slick. We only have one prototype. Now, what's happened, and Jane and Simon, you know, I wrote you about this, is then I looked at it and I'm like, well, look, if we're importing the electronics and the solar panels from China, and we're importing the vacuum flask and the stainless steel inset from China, now we're dealing with the thing where, like, if we just assembled them with China, it would be cheaper, and we might as well just import them all together. And, you know, I mentioned this, and my anthropology student, like, just was horrified. She's like, you're just throwing away everything that you've been talking about and teaching in these classes. And I'm like, I get it. Yeah. And so this is kind of disturbing to me. But I mean, I don't know what it would entail to get a vacuum flask company in Africa or India, but that would also be an industrial setting. So there's a whole bunch of stuff going on, and I'm willing at this point to say, I don't know what's going to happen. Let's just study and learn.
Oh, okay, thanks. No, it's great insight. We have another question which relates to the performance of the solar panel and whether you've tested the performance in a typical tropical rainy season. And then additionally, has the product been marketed as an addition to household cooking stack or as a replacement for the cooking stack? And if it does need to be plugged into the mains, how does the performance compare to other electrical cooking technologies? So there's 3 questions wrapped up in that. If you want to kind of address the first one about the performance of the panel in a typical tropical rainy season, if you've got any experience of that.
So I could respond to the 3 questions kind of together. I have a 12-volt power supply that I hook to main, and so it gives me about 35 watts, and it keeps it hot all night and actually heats it up, and it's fine. If somebody wanted to do that, and they're inexpensive. Even when you buy one, they're only $10. So it really is a very good answer for people who have electricity but still cook with wood. In the rainy season, it's not going to work, or it'll work much less. It just depends on how many hours of strong sunlight you get during the rainy season. And as far as marketing, we're not marketing yet. We're leaving that to the local enterprises, and they aren't at marketing. They're reaching out and they're talking, and yeah. So John.
Yeah, I can say what it's like in a rainy season. Our field trials coincided with the rainy season, which wasn't helpful in one respect, but it was in another. Sometimes, if you have heavy rain, you then are followed by sunshine, and that is that works, because obviously when you get the sunshine, you get the power, you can then get the heating, and because we've got the phase change, you maybe not get as much, but you get some. The bigger problem is when it's overcast, and then it tends to be more difficult to get the temperature rise that you're looking for. So yeah, we can't invent energy. We have to wait for some, but obviously the better the solar panels, the more solar panels, the easier that equation becomes in difficult conditions. As far as household cooking stack, I have to acknowledge my ignorance here. To some extent, I'm not quite clear what a cooking stack is, but I think it means a variety of different methods of cooking.
Different cooking technologies. Maybe you have some gas, maybe you have some wood, and they have the solar cooking.
Well, the people that we were interfacing with all have charcoal as their baseline. The wood and charcoal is always available to them. The problem is it's getting more expensive and more difficult to find. But it is their baseline, and I would predict that the evolution of this technology will be that it will be a component in a suite of cooking methods, depending on circumstances. So, in the rainy season, yes, they'll probably use the charcoal because it's more reliable and more efficient. At other times, however, there will be a solar cooker because it's a lot more pleasant. One of my experience has been in cooking with the open fires, and I have some lovely pictures of me looking as if I've been crying my eyes out for 45 days because it's so unpleasant, and I was only in there for a few minutes, and it's hard to predict the niches which are going to grab the imagination, but for example, one of the entrepreneurs ladies that we worked with was using a deep fat fryer, and she took out her donut type products and sold them for cash every day and made a lot of money. In her terms, it was her livelihood. Now, if we could give her a deep fat fryer that works at about 150 and stops her having to live in a smoke filled room for several hours a day, then I think she'll do it. And if she can't, if the weather's not good, she'll use the fire. I see that's probably the sort of thing. And then, you know, if she's using it, then somebody else will have a go. That's how I think it'll probably evolve. And it's very hard for us sitting where we sit to really understand that. The key to it is getting the kit into their hands and then seeing where it goes. Was there a third question? Have I plugged in? Yeah, I think the performance issue is enormously dependent on what you're cooking. I think with experience, they will find slow cooking, long-term cooking, sous vide cooking, whatever you want to call it, will become part of what they can do once they've got the kit to do it. Then if you wanted to brown off your onions quickly, they might light a few charcoal stoves. Because, you know, if you want a really hot, crispy fry up, then you need, you know, instant heat sort of thing. But that could be LPG, like it was discussed yesterday. It could be biogas, which is something that some people, you know, are considering, because, you know, a gas cooker is a very good way of getting an instant high temperature. So, and that could be from other organic sources locally. It's difficult to know. The key thing is obviously that we've got to get it out there and under test. So.
Okay, great. Thanks, John. So Pete, we've got a little bit of time. I wondered if we could go back to your breakfast and see whether it's cooked.
I can't compete with that.
Can you see it all right?
Yes.
Oh yeah, man, this is looking, it looks like I overcooked it a little bit. You can see the onions are very browned and the broccoli is, it's not very crisp anymore, but I mean, that's my own fault, right? I was just so excited about the discussion. So I'm going to pull it out right now. And you can go on with your next question if you have one.
Could I just interject if there's a space while I remember? One of the insulation materials that I'm working on at the moment is taking corn, as in sweet corn, and popping it, as in popcorn, and combining that with cooking foil, which they do have available in Malawi at the moment. And I'm pretty excited about that as a potential insulant package. But I'd be interested in anyone else that's got any other ideas of in how to make insulants from raw materials in these communities.
So John, we experimented with rice hulls, and yep. They smolder. We started a fire, and got in big trouble. So that's my experience. I'd be careful if it burns.
I wasn't hoping to get them that hot.
Okay.
So there's a comment in the chat actually which says that wood ash works fairly well.
Wood ash?
Wood ash.
But interesting. That's available. Keen to explore. I'm trying to understand why. Well, Benjamin, perhaps you could explain a little more how it's been used.
Benjamin, feel free to unmute.
Yeah, of course. It is used in Nepal as insulation instead of ceramics in high altitude communities.
As a powder, sandwiched between two surfaces around the cook pot. Is that the sort of idea?
Yeah.
Okay. Thanks for that. That's interesting.
You know.
If I could interrupt for just a moment, I want to express something about the use of this. So in my picture, I showed a separate cook pot that you can pull out. And I actually choose not to do that because it inhibits the heat flow because you have to go from one metal surface to the other. So I actually cook the food directly in the phase change assembly. And then the issue comes with cleaning. And one of the things I found is that I just have to wipe this out between uses. So because if I leave oil in there, it'll bake on and it'll smoke and it's really nasty. And so if I just clean it every time I use it, you can see that I have this little tube and all the condensate comes out elsewhere. And so Now, this is probably going to have cultural pushback because, I mean, for me, there's no health problem with that because this is always hot. There's not going to be, you know, I don't have to be clean, and it's really very clean. But if people feel they need to scrub shiny, then this is going to be a little more of a challenge. And so again, some of the innovations was I had to find this kind of spoon to scoop things out because people are used to being able to grab the pot and dump stuff. And so it's just little things like that that become important. Thank you for letting me interrupt.
Well, no, that's fine. I think Simon has a question that he'd like to ask.
Yeah, I'm going to ask it verbally because it's slightly complex. So, John, I know that you've worked with biogas, and certainly there are explorations of communal supplies. Can you envisage a central phase change battery charging area where basically people could get their phase changed battery changed by something like a biogas unit or a mega solar array, and then actually just take it to their home once a day to cook with in the evening? And Pete, comment on the idea as well, please. And just before I sign off, presumably the popcorn works because it traps the air. Is that your rationale, John? Yeah.
Yeah.
Okay, thanks. So communal charging of phase change batteries?
Yes, I think that may well be a direction of travel. Whether you bring phase change to the heat store or whether you actually just bring water and have your water raised from ambient up to 80 or 90, and then you put it on your charcoal fire for finishing off, whether or not we have a large store of hot water. I mean, for example, in Malawi, a third of the children in Malawi get their only hot meal cooked for them by centralized cooking through a charity called Mary's Meals. This is a vast operation. I think I've made some calculations how many tons of wood a day they use to create that feeding operation. So if one had the right connections, you could make big inroads on wood use by tackling a few large sort of institutional type settings. So yeah, I think there's a lot of possibilities for making fairly quick movements in that direction through
the problem I have with
village centralization.
The problem I have with getting water to warm and then take it home and finish it off with charcoal is you're still lighting a charcoal stove. From a health point of view,
yeah,
as soon as you light that charcoal stove, you haven't made any gains. So that's surely the phase change battery to finish off the meal is significantly better if it avoids lighting charcoal at all.
The reservation that I would have, and we could go on at length, I guess, would be you've got a substantial asset that you're providing a service. You could certainly provide a phase change, a molten phase change battery and dump it in your cooking pot, for example, which was one of the options we looked at, because you can get heat resistant pouches and things where you could easily see that happening, and we did some trials on that. But somebody's got to own the phase change installation, and then somebody's got to figure out how you get paid to manage that, and so it becomes more complex from a sort of human perspective. My view is don't rule anything out. Let's try them all. Let's give them some air, see what flies. There is no right answers in this game at the moment, from my point of view. I don't know, Pete, do you want to come in? Have I answered your question, Simon?
Yeah, sure. Thank you.
So I have two things to say. I had some students study solar ponds, and that's a way where if you put down a layer of insulation and then about 10 centimeters of water and run a pipe through it, And that will get very hot during the day, even in San Luis Obispo. And so you can get the water up to 60 or 70 that way, and then top it off. And this would be really inexpensive. But as far as a phase change delivery, you might look up. Have you ever heard of solar buckets? BUCKETS. That's being developed and advertised by a university group somewhere in Illinois, I believe. And I found it pretty infuriating because I contacted them and said, I want to refer to them in my paper. And what could they send me? And they said, yeah, you can refer to us, and you can find nowhere what their technology is, what the phase change salt is that they're using, how it works, nothing about it. But they're talking about doing exactly what you want to do, Simon, is they have a solar concentrator and they put this bucket at the focus, and it gets really, really hot, and then they bring it in to their house and they cook on it. And
so we also funded them as part of the TRID Challenge Fund. And yes, we had some frustrations with the administration and communication. But interestingly, what we funded was moving away from solar concentration to PV electrical heating. So they have their sun bucket, which, as you say, is a much higher temperature. I mean, it operates at 350 degrees and what is the molten in salt inside, I don't know, but yes, yeah.
It's probably a potassium nitrate or something like that, or sodium nitrate.
I looked into it a little bit, and I think I have a clue what it might be because the temperature is correlated, but that's a guess.
Oh, okay.
But they also report big issues with corrosion, which you'd obviously expect at those temperatures. Yeah. But as I say, don't say boo to anything at the moment. If I just could pop back to one of the questions I saw in the chat about the crystallizations, that to me was you struck the nail on the head. During the cooling, there is an issue of how to encourage the heat to come out from as it starts to cool, it crystallizes, it then becomes self-insulating. And I know that Pete's done some work with aluminium. We did some work with other metals like shredded, cut up aluminium cans, beer cans. We also looked at integrating the PCM stone, with the stone acting as a sort of a heat conduit to even out the temperature. There's lots of mileage yet in that discussion, I think, as to what you can put with the PCM to encourage the heat exchange. And to stop it self-insulating. It's great if you want slow cook, but it's not so good if you want to deliver the heat quickly. I don't know if I've answered the question that appeared earlier. I hope so.
Yeah, I think so. I don't know if you've got anything to add, Pete. We're always kind of at the end of the session, but if you've got anything to add, that'd be great.
I'm good.
Okay. So two other comments, I think. So one from John, who talks about his experience at Crest of if cooking time is about 1 hour or less, an air gap of 2 centimetres is pretty good, at least as good as 2 centimetres of insulation. And then on a separate note, Ben notes that the wash sector has done quite a lot of research on community-led sanitation models, and there will be some cross-sector learnings that might be useful for the energy sector. So I guess, Ben, if I can connect you with John and Pete, and you can kind of share that information after this seminar is finished, that'd be great.
Yep, very happy to do that.
Okay, I think we've just got one. So, and one last comment, I think, from John Leary. Great to see so much discussion on exactly how each type of food needs to be cooked and optimising the technology around this. A major focus of our work in the culinary theme of MECS is to understand what country context and how. This seems particularly important for direct solar and PCM cooking devices. It's excited to work with you to explore which contexts the devices you're developing may be best suited for, based upon which foods and preparation techniques are most popular locally. So John's been kind of instrumental in the cooking diary studies, of which I think there's 3 countries that are profiled on the website under our publications section. So again, kind of hooking up with John would be hopefully beneficial to the both of you, or the 3 of you, to kind of develop this moving forward and gain some insights from each other. So we've kind of run over time, but it's good that kind of the questions have been coming and we've managed to answer them all. So I'd just like to thank both Pete and John for their time this morning, and for everybody attending today. As we've noticed previously, this session has been recorded and it'll go online in due course. But thanks very much for your insights and an introduction to your projects, and good luck with moving them forward. Yes, Pete.
In response to John Leary and anyone else, the first step is really obvious to me, and that is everybody's welcome to join our international learning community meetings. We're going to start in 4 hours, by the way. We meet at 10 o'clock Tuesday morning.
Pete, have you got can you circulate the link to that in the chat room, and then if people want to join?
I'll do that. But I don't know how to leave a chat.
Okay, so I can kind of run through that with you.
Okay, let me copy the link first.
Okay.
And, I'll get it here.
So the icons at the top, if you kind of move to the left, and there's like a speech bubble.
Because I can see the chat, I just don't know how to enter it.
There should be a blank box at the base that says type a new message, and then you can just enter your text there. The other thing you could do is get the link on your screen and then share your screen, which would mean it would be available on the recording as well.
Mm-hmm. Okay, so where is chat? Show conversation?
Yep.
Oh, okay. Show conversation, and then where does it say enter? Enter to type new message. Thanks.
That's the one.
I tried to. Did I do it?
And then you enter. Yep, that's come up. That's great.
Yeah.
All these platforms are subtly different, so that you kind of know how to use one, but another one is just completely different. So no, that's great. If people are interested and want to join Pete on that later today, then feel free to connect.
Yeah, I think and maybe the first step would be, because we do meet, and we're going to change meeting times, so rather than focus on the link, it might just be best to take my email and I'll get you connected.
That's great. Thanks, Pete. Okay, so I think we're going to leave it there now. We've kind of run over by 10 minutes, but thank you all for your time, and look forward to seeing you in other sessions.
Thanks, everybody.
Okay, bye-bye.
Thank you so much. Bye-bye.